Good evening to all. My name is Eleftherios Petavratzis, and I am PhD candidate in the Laboratory of Nonlinear Systems, Quick Complexity at the Department of Physics. Today, I would like to discuss about the topic that we are currently working on, and it refers to the use of chaotic mobile robots for exploring a given area. With this presentation, I'm gonna talk about chaotic systems and how they can be used in order to control the motion of an autonomous mobile robot. And next, I'm gonna show you a robotic platform that we have built. As I said before, our main target is to construct a strategy that can move a robot in order to explore a given area. Of course, we want additionally our robot to move randomly inside this area. So in order to do that, we decided that we're going to create a chaotic random bit generator. For the first stage of this study, we have to select the appropriate chaotic system. In our case, we use the logic map, which is a one-dimensional discrete chaotic system. And it is very easy to use in this type of applications. Here you can see the bifurcation diagram of the chaotic of the logistic map, and you can notice that our system for values until 3.5 it shows periodic behavior, and after that point it shows a chaotic behavior. Here we have the histogram of the logistic map, and I think you can notice that in these two axes of the histogram, we have the majority of the values of the logistic map. So, in order to create bits that are truly random, we decide that in these two regions, we're going to use a modulo operator. The rest are produced with the way that you can see over there. Of course, we managed to create a bit sequence, and we want to test it if it is truly random. In order to do that, we use the FIPS, the NIST statistical suite, which has 15 different tests. As you can see, all of these tests are successful. So we are pretty sure that our sequence is truly random. Next, we took the pairs of bits of this sequence and we created the motion commands for our robot. Our robot can move in 4 different directions, as you can see over there. And of course, in order to avoid the collision with the boundaries or the obstacles of the workspace, this robot can turn 45 degrees either clockwise or counterclockwise. Of course, sometimes we want to surpass these obstacles, and for that reason, we are using the values of the logarithm of a new logarithm map in order to give us the order in which way our robot can move. Here, I'm going to show you the Alphabot platform that we are using. As you can see, this platform has 2 wheels in each side. There are 2 batteries that can give power to our platform. And at the top, you can see an ultrasonic station that can turn into 3 different directions. This station can send pulses up to 5 centimeters and can detect the placed obstacles. Of course, there is an Arduino Uno microcontroller that is used in order to control all the platform. And this microcontroller has an USB port that can be connected with the PC that we are using. It has 14 digital and 6 analog pins. And of course, it can be programmable by Arduino IDE, which has a language that is very similar to C++. The ultrasonic sensor that we are using for the detection of the obstacles has 3 basic limitations. It is very sensitive to variation in the temperature. That means that when the temperature of the environment is changing, then there is a chance that we have false measurements for the distance of the placed obstacles. It cannot detect the thin, soft, and small objects. And of course, the third and most important limitation is that sometimes when the reflective angle is very small, our sensor cannot detect the place obstacles. In order to solve that problem, we decided that our sensor can move into 3 different directions. Here you can see the rotary encoder that we are using in our wheels. It is divided into 3 basic things. We have a disc that can rotate it. On one side, there is a LED, and on the other side, there is a photosensor that can detect the lighting from the LED. We know that one full rotation of our wheel is equal into 40 light detections. Of course, these 40 light detections are equal into 21 centimeters distance, according to the size of the wheel. But in our case, we want our wheel to move into 30 centimeters. So, in order to do that, we have to have 57 of these light detections. Here you can see the parameter set of our given workspace that we are working on. Our workspace is divided into cells into 70 cells that have each cell has a 33 square centimeters size. Here you can see how our robot is working in the workspace that we have built. You can notice that our sensor is moving into 3 directions, and also with this motion, our robot cannot hit with the boundaries of our workspace. Here I'm going to show you the coverage progression of our method. We measure the coverage rate in each minute of our study, and you can notice that the coverage rate is becoming greater in each minute that is passes. And at the left bar at each side, each figure, you can notice that it is actually the number of visits in each cell. Here we have the statistical analysis of our method according to the initial position. And you can notice that the change in the initial position reflects the coverage rate of our given method. And the same thing happens when we are changing the distance from the obstacles. You can notice that when the distance is becoming greater, then the coverage rate is decreasing. So, to conclude, we can say that our robot can move chaotically. The distance from obstacles or boundaries plays a crucial role for overall coverage, as you can notice from the statistical analysis that we have done. The time duration of robot's operation varies from 18 to 21 minutes, and it depends on how charged, if our battery is fully charged or not. And as a future work, we're going to implement, we have created some methods that can improve the overall behavior of our robot, but they are in a simulation mode. Our next step is to use these methods into the robotic platform. And of course, we're going to use this platform not only in our laboratory, but actually in the real world. Thank you very much and for your attention.